Hello everybody! We are going to continue with the topic of SoftMotion in ctrlX. In this second part of the manual, we will be able to start the system with 3 simulated axes. To begin with, we are going to create an example program with 3 virtual axes in simulation mode. All the examples that we are going to see are made in ladder format for a more understandable visualization of the system. Although obviously later each one can use the programming language with which they feel more comfortable. For the example, we will add 3 axes of virtual type to which we will change the name, leaving them as follows: x-axis, y-axis, z-axis. The simulation option allows us to use the system without connection to a real axis and test the program. The program example is made in different folders, each one of them with the different modules for the control of the project. In this first part of the project, we will only need the one hand to activate the power in the axis simulated and the reading of the current position. Obviously, as can be seen in the structure, we will also use a folder for the machine programs generated from the software, the module for controlling the movement interpolator, and the last one with which we will configure the movement viewer on the screen. We also have a table of general variables. First of all, we have the general variables that we are going to use in the example. Activation bit for the power modules of the axis. As it is a 3-axis operations system, the power will be activated simultaneous on all of them. Signaling of axis with power activated. Start and stop activation bits of the CNC program. Current position of the axis extracted from the position reading modules. Error control bit in the modules for automatic positioning of the axis. If B with a structure for the control of the positions on the track of the visualization on the screen. In the axis control folders, as we have already mentioned, at the moment we only use the option to activate power and the reading of the current position. These 2 modules are located in the SM3 basic library. The next part of the example project is dedicated to the interpolation module. The interpolation includes several different modules that, as we will see below, are linked together and are located in the following library. These modules are SMC Interpolator, SMC Trafo F Gantry 3, SMC Trafo Gantry 3, SMC Control Axis by Pose. The structure for the interpolation can be seen in this image. The interpolator is in charge of managing the program and other data that we will send to the transformation control. In the example, the correct module for the transformation of the CNC program is SMC Trafo Gantry 3, which sends the destination positions to the axis through the SMC Control Axis by Pose modules. Overview of the SoftMotion component structures for the CNC editor. Description of the interpolator inputs. In the image, we can see the bit for the start of the program, the one from the stop of the program, and very importantly, the one for the assignment of the machine program that we will want to execute that must be used with ADR to be interpreted correctly. This last input in this used may vary when using a program for the PC or from ctrlX core, since the way to make the call is strictly different. Interpolator module. Descriptions of inputs. Part 2. Be slow, stop. In through state, the SMC interpolator will be made to slow down to 0 according to the velocity profile defined in eval mode and the maximum delay of the current SMC geoinfo object, and wait until B slope stop is reset to false. B emergency stop. As soon as this input becomes true, the SMC interpolator will cause an immediate stop. This means that the position will halt. Therefore, the speed will set to 0 immediately. B wait at next stop. As long as this variable is false, the false value, the path is paced non-stop. Otherwise, the SMC interpolator will be made to halt position at the next regular stop. That is, at position points where velocity is 0, usually at patched angles, and stop until B wait at next stop is reset to false. D override. This variable can be used to control the override. The override is not allowed to be less than 0.01. The programmed speed of particular objects will be scaled by the override, and therefore the set speed can be increased or decreased in online mode. For example, the override equal to 1, default value, cause executed speed to run, while the override equal to 2 will double them. Be careful with this value if we are working in simulation mode or with real access. In general, in simulation, we should have it much higher than with the real access. The WI post time. This variable must be set for each call. It represents the cycle time in microseconds. By default, we are using 3000 in the example. Interpolator module. Descriptions of inputs. Part 3. The last Y pose. This input allows the user to measure the leg of the route that is being pulled by the interpolator. The output dy pose is the sum of the last Y pose and the distance traveled within the current cycle. If the last Y pose is set equal to output dy post, dy post will always be incremented by the current path segment, resulting in the total length of the path traveled. The last Y post can be reset to 0 or are different valued at any time. B abort. This input set to true will abort the function block and reset the outputs. A rising edge of B execute is required to start the interpolation again after aborting. B single step. This input caused the interpolator to stop at the transition between two path objects, also in transition with identical tangents, for the duration of one cycle. If B single step is set to true during motion, the interpolation will stop at the end of that object. which can be reached without exceeding the programmed deceleration value. If the interpolation must stop at the next possible stop position, at points where velocity is 0, then b wait at next stop must be used. B acknowledge m. This input can be used to recognize an m function. If the input is true, the W output will be cleared and past processing will continue. Interpolator module, descriptions of inputs, part 4. Bell mode. This input defines the velocity profile defined in SMC int bell mode. By default, the interpolator uses the trapezoid mode. Interpolator module, descriptions of inputs, part 5. B kick stop. If this input is true, the interpolator will slow down to 0 until B kick stop is reset to false. The reduction is done according to the defined speed profile, peel mode, and the deceleration given by the maximum of T Kirk deceleration, and the delay currently programmed in the path. If a square rate mode is used, then the jerk is limited by max, D jerk max, and D kick stop jerk. D kick deceleration. Deceleration value used for B kick stop. D jerk max. Maximum allowable jerk magnitude. Only used for quadratic rate modes. It must be positive and cannot be changed while the interpolator is running. D kick stop jerk. The value of D kick stop jerk is used by a kick stop to reduce acceleration in one of the quadratic velocity modes is selected. B suppress system M function. If this option is set, the WM output will be not set for internal in function created by the G75 or G4 commands. Interpolator module, description of outputs, part 1. B done. This variable will be set to true as soon as the input data with machine program has been fully processed. The function block will not take any further action until a reset is performed. If the bexecute input is false, then B done will be reset to false. B busy. True while the execution of the function block is not finished. B error. True while the execution of the function block is not finished. W error ID. Active fault. PI set position. It reflects the calculated set position and contains the Cartesian coordinates of the next position, as well as the state of the additional axis. Is MC post info. Interpolator module, descriptions of outputs, part 2. I status. This enumeration variable reflects the current status of the function block defined in isMC int status. For example, IPO axle, IPO decel, IPO weight, etc. Interpolator module, descriptions of outputs, part 3. P working. This output should be connected to the enable input of isMC control axis by pos. Will be true if and only if list processing has started and has not yet finished. I act object source number. Value of e source line. No member of the active isMC info object of machine program GE. If B working is equal to false, the value is set to -1. The actual object length. The length of the current object is only valid if working equal through. The actual object length remaining. The remaining length of the current object is only valid if working equal through. The vel. This variable contains the current trajectory speed. Interpolator module. Descriptions of outputs. Part 4. Vector actual tangent. This structure contains the tangent of the trajectory. Last switch. This output contains the number of the last switch passed. W switches. This D word describes the current switching state of all switches 1 to 32. Bit 0 of the D word represents switch 1. Bit 31 represents switch 32. Unlike last switch, this bit field will also have multiple switches in a cycle. D way pause. See the D last way pause entry. WM. If the interpolator passes and the M function, this output we will see to the value associated with the M function. The interpolator will stop until the M function is acknowledged by the B acknowledged M input. AD tool length. Parameters for tool length compensation set by G43, I, J, and K. Actual object. Pointer to the currently interpolated path element. Possibility to 0. The following module allows us to extract the position sent by the interpolator, and that we will use later to send to the axis. The module also has 3 input values that allow generating a displacement in the position of the axis. On page 10, you can see the connectivity between the different modules. The last of the modules is in charge of generating the movement of the axis. This page contains the description of the inputs of the axis movement module. In the image, we have the x-axis control module. The other 2 axes have the same functionality, and only the name of the axis should be modified in this case. As can be seen in the image, some of the data comes from the interpolator and this other from the transformation module seen previously. All the other values are modified, although it is recommended that all the axes operated with the same operating values. The values of speed, acceleration and deceleration must be taken into account according to the operation mode where used, since the behavior in simulation mode is slightly different from the use of real axis. Description of the motion module outputs. At the output level, we have the most common activated, aborted, errors, and another that is used to generate an emergency stop in case of error, and that if it is being used on the interpolator module using an error control generated from certain states of the 3 axes of the system. In the following folder, we are going to establish the data to show the visualization of the executed CNC program. For this, we will use the isMC position tracker module that will allow us to show the path of movement on a screen. The module to generate the path on the screen is located in the visualization toolbox, and more specifically in SM3 CNC. To enable it, we must use the structure defined above and that should be placed in the output of the SMC precision tracked module. The machine program can be managed in several ways. Program located in ctrlX PLC Engineering, program located on the PC or in ctrlX Core. We will start by using a machine program generated from the software itself. First of all, we will create a folder that we will for the CNC program, or whatever we want to call it, and insert a program of the type CNC program. Example of program created from SoftMotion itself. Additionally, the movement points can be modified from the lower screen so that the trajectories can be done manually once the points have been generated. The program must be called in this case in the following way and through the EDR instruction. When creating the first internal program, another module is also generated that allows us to make some optional selections. Some of them are also part of the interpolator. We can also see that a section appears where certain function blocks that are being used in the program are shown. The example shows one that we will use later. This is a first representation of the system, in which we can observe the operation of the simulator with a program generated from the SoftMotion software itself, and another from an external program. We will detail this last option in part 3 of the CNC SoftMotion manual.